so now by measuring different relaxation rates in our spin system, now we will be able to probe the spectral density function at the eigenfrequencies of the spin system. Okay, and so what are these eigenfrequencies? Where if we are looking at a system that is 1 nitrogen 15, 1 proton, we'll have 0, the Larmor frequency of nitrogen, and the set of frequencies that are around the Larmor frequency of the proton. Okay, and if you have a system that is, say, a small protein with a correlation time of the order of a few nanoseconds, then the spectral density function at the Larmor frequency of nitrogen will be just in this dispersion region where you have a strong decay of the spectral density function. Okay, now I will not get into the details of the calculation of relaxation rates. I will just show you the results. So in this system of two spins, we can obtain expressions of the transverse relaxation rate and the longitudinal relaxation rate. And what I would like to point out is that the transverse relaxation rate will have here J0 that appears. And so since this is in general the largest value, this will be often dominated in macromolecules by J0. Whereas for the longitudinal relaxation rate, you don't have J0. And so often it will be dominated by J omega n. So the spectral density function at the lowest frequency. So one small point when we are looking at the spectral density, a few characteristics. So if we get towards 0, then the spectral density function becomes proportional just to tau c. So the larger the system, the longer tau c, which varies with the volume of the molecule, and so the higher J0. So in a very large system, the relaxation is completely dominated by J0. Now this transition, this inflection here on the decay of the spectral density function takes place at a frequency that is about the inverse of the correlation time. And so the smaller the correlation time, the higher the frequency of this transition. Okay, and in the end, the spectral density at high frequencies now will decay like the square of the frequency, but will also be higher if the tau c is smaller. Okay, so once we have seen this, I will present to you a set of high field data that we recorded a few years ago as an illustration. Okay, so we recorded those on a partially disordered protein, actually a small construct of a transcription factor called Engrailed. That was very nice for, I think, very nice for illustrative purposes. So we have a homodomain with 3 alpha helices that are well recognized here by secondary structure propensities. And we have a disordered N-terminal extension with here quite hydrophobic hexapeptide located in the middle of it. So this is a very nice system to look at various regimes of dynamics. So when we measure, for instance, longitudinal relaxation rates, you can see that they do not vary with time very much in the disordered region. However, we have a very strong dependence of the rate with the magnetic field in the folded region. And this is really because J omega n is just sliding down this slope here as we increase the field. So here, this is a node that actually the R1s is a very good probe of motion at around nanosecond timescales, which correspond to the overall tumbling here of this small domain. Another type of rate that we always record are, or that we try to measure are dipole-dipole cross-relaxation, so the NOE effect. So when you have a dipole-dipole interaction between these two nuclei, and that leads to an exchange of polarization between the two nuclei, like in the NOSI experiment. And this is really the NMR equivalent of a FRET experiment in particular. Okay, so in this case, what is important is that this rate only depends on the transition at 0 and double quantum, and so on spectral density function here at the difference and sum of the two frequencies. And so it means that in this heteronuclear spin system, we'll have only high frequencies that are probed by this rate. So it's a good way to probe singly high frequencies. So we do not measure it in a transient manner, like in the NOSI experiment, but in a steady state experiment where we saturate the protons and we look at the ratio of intensity that comes from longitudinal polarization of nitrogen in the saturated experiment or in the equilibrium experiment. And you have this well-known expression of the NOE ratio. So why do we do this? We do this in particular because you have this factor gamma H over gamma N that equals to -10. And so it amplifies by a factor of 10 the effect of sigma, this very small cross-relaxation rate. And so what we have here is not just in this NOE graph is not the cross-relaxation rate, but it's the ratio. It's something that comes from the ratio of this cross-relaxation rate and the longitudinal relaxation rate of nitrogen. So it comes from really how much the spectral density function will decay between omega n and omega h. And so it decays a lot if you're in a small folded domain. And so this is why this factor is small and the NOE is close to 1 in the folded domain. However, you see that the decay is much smaller, and it really changes at the relevant frequencies here, making the NOE a great way to probe, in this case, dynamics that dominate the motions of the disordered region. Okay, the final type of rate that I want to discuss are cross-correlated cross-relaxation rates, in particular the one that comes from cross-correlation of the CSA and the dipole interaction. So in this case, what we're actually considering from the beginning is how an interaction, let's say, builds on itself. So how an interaction is correlated with itself. But sometimes two interactions can play hand in hand. And this is the case, for instance, if you're looking at just the single transitions of nitrogen-15 that correspond to the proton in the alpha state. In this case, the CSA interaction and dipole-dipole interaction play hand in hand, and they actually work together to make relaxation faster. Now, if we change the state of the proton and go from the alpha state to the beta state, then somehow we invert the dipolar interaction. And so if these interactions were adding up in the alpha state, then they will actually subtract each other in the beta state. And so in this case, we'll have slower relaxation. And this is what is very nicely exploited in the Troisi experiment. So what we will have is what's called differential auto-relaxation of the two components of the doublet. So if we start with a nice in-phase doublet of the nitrogen-15 with each transition that corresponds either to the H alpha or the H beta, what we will see is one that decays faster than the other. So the one for the H beta, the state alpha for the proton, than the one for that corresponds to the beta state for the proton. So we can represent this as a difference of auto-relaxation rates for these two transitions, but we can also represent this in a different way, saying that this now asymmetric doublet is actually the sum of an in-phase doublet and an anti-phase component. And so this cross-correlated cross-relaxation effect leads to this relaxation interference that we see here, but also can be represented as just cross-relaxation between the in-phase and the cross and the anti-phase coherences. And this is actually the way we measure it. In particular, I would like to point this very nice work introduced almost 20 years ago by Philippe Pelupessy, where we measure all four relaxation pathways in the system of two operators. And this is a very good way to obtain a very nice and accurate measurement of this cross-relaxation rate. In this case, the transverse CSA dipole cross-correlated cross-relaxation rate is dominated by J0. And so this is a very good measurement of order. And you can really see how, for instance, this hydrophobic hexapeptide pops out here of the disordered region. Okay, so now we end up with actually many rates, about 20 relaxation rates per residue in this protein. Since then, the team of Martin Blackledge has done even more by adding temperature as a varying factor. But this is already a large number of rates. And the question we had when we had all these relaxation rates, so longitudinal relaxation rate, NOE, transverse and longitudinal cross-correlated cross-relaxation rate, was what to do with those, how to analyze them. So what is typically done to analyze relaxation rates in a protein is to use the model-free approach. I mean, it was introduced now almost 40 years ago by Lipari and Szabo, and it was a very nice way to do a quantitative analysis of relaxation in a way that we would not have to debate for too long about what is the exact nature of the motions. And so the type of parameters that we obtain, if we consider the internal correlation function, is the order parameter, that is the limit at long times of this internal correlation function, and an effective timescale for those internal motions. Okay, so this is very nice, but I mean, since then, lots of variations have been proposed, going from 2 timescale, one for overall tumbling and one for an effective timescale for internal motions, to potentially 2 timescales when you have internal motions that take place both, let's say, on nanosecond timescales and picosecond timescales. Many approaches have been proposed to introduce distributions also of correlation times for internal or global motions, or even some approaches like the slow relaxing local structure and propose when you have a coupling between the different types of motions. But all of these were mostly introduced in the context of folded proteins, where one of those correlation times is the one for overall tumbling. And in a disordered protein, this is an issue. In particular, in a disordered region, it's difficult or impossible to define an overall of what would be overall tumbling. So if we consider that in a disordered protein, we do not know what is a priori the distribution of correlation times, then what we decided to do is just to try to reconstitute without a priori knowledge the distribution of correlation times. But of course, this is an ill-posed problem. And so what we decided to do is to take a very simple regularization approach by discretizing this distribution. So what we have now will be just an array of correlation times of a range of about 3 orders of magnitude of correlation times. And we will just optimize here the coefficients for the various correlation times. So how does it look like? Well, sorry, we're just optimized using statistical arguments the number of correlation times with their spacings, and also what is exactly the range of correlation times that is probed. And here you see a slight preference here for an optimal, where we use 6 correlation times going from 21 picoseconds to 21 nanoseconds. So I'll just show you one nice schematic representation of the results that we call somehow the barcode of dynamics of our protein, And here it will be a representation where the larger this band, the larger the histogram band, the more coefficient given for a given time scale. And so what you can see is that basically the dynamics of the folded domain is highly dominated by the overall tumbling on the low nanosecond timescales. Whereas, as shown also by others like Art Palmer and Martin Vakledge, you have a dominating timescale in the disordered region around 1 nanosecond. With some components here, you remember here this hexapeptide that are, you see that there is more density here in the low nanosecond regime. Okay, and this correlates very well with the structural features. Okay, so in this more introductory part, I showed you that measuring a series of rates at a series of magnetic fields was a good way to probe motions at different sets of frequencies. And we can think maybe beyond the typical model 3 approach to analyze this data. I would say that to go beyond impact and to do this type of approach where we really look at what correlation times contribute to relaxation, I invite you to pay a lot of attention to Andy Smith's talk just after Chris's, who will show you a really rigorous way to do this using the detectors approach that we worked on a little bit together. And I really will let him introduce this approach in about half an hour or so. Okay, so before I let Chris and Andy speak, I would like to tell you a little more about magnetic field dependence of relaxation rates. You see here, we vary the field between 400 megahertz and 1 gigahertz. And you see that this is actually a good way to probe nanosecond timescale motions. You have a strong variation of the longitudinal relaxation rate. But can we do better? And to do that, to probe slower motions, what we would have to do is to lower even further the field, all the way to magnetic fields that are actually too low to do high resolution NMR, particularly on the protein. And so the solution for this, obviously, is to do relaxometry. Yeah, if I show you again here now, if I want to record nitrogen 15 relaxation between a 400 megahertz and a now 1.2 gigahertz system, I will cover some significant ranges of frequencies, but there will be gaps here and there where we'll just cannot probe the spectral density function. And so the solution for this is really to measure relaxation at lower fields, but we want to do this without giving up high resolution. And so the solution for this was introduced by Redfield and others like Bob Bryant about 20 years ago. The idea in particular of Redfield was to use a commercial high field system and to add an apparatus to move the sample in the stray field and use the stray field of the magnet as a variable field. So you polarize your sample at high field for sensitivity, you move the sample to a position of the stray field for relaxation, you relax for variable delay, so you have a nice relaxation decay at low field, and then you come back to high field for detection with high resolution and high sensitivity. And this way, if you add a few measurements, then you can actually describe the entire spectral density function. So we've been doing this for a while with Bruker with this prototype that was developed by Thorsten Marketsen and Frank Engelke. It's a pneumatic system. The sample moves at about 10 meters per second. So it's very fast. On the other hand, it's not very sensitive. You see the active volume is 60 microliters and the fitting factor is not very good. So the reason why I'm at Bruker this week is actually to probe a new system that is actually as sensitive as your NMR spectrometer at home. So because it's not very sensitive, the data we have are only on model systems, and what I will tell you in the whatever number of minutes I'm allowed to speak is an investigation of sidechain motions in ubiquitin. In particular, we focused on the 7 isoleucine residues in ubiquitin, with using labeling to have a fully C12 and deuterated background and only, sorry, 1 carbon-13 and 1 proton here at the delta 1 position, at the delta 1 methyl group. So if we run a 2D spectrum, we see this nice resolution, these 7 signals. But here, this is not typical HSQC. In this experiment, we had 50 millisecond relaxation delay at a field of 4 Tesla. We can decrease the field even further, all the way down to 0.3 Tesla. And you can see that we can still record some nice high resolution 2D spectra of good quality. However, here relaxation took place at 0.33 Tesla. So this is a Larmor frequency for proton of 14 megahertz. So we really recorded relaxation rates all the way up to 22 Tesla on a 950 megahertz system and all the way down to 0.3 Tesla. And now what we obtain is for each of these 7 meteor groups in ubiquitin, we obtain a full nuclear magnetic relaxation dispersion profiles with about more than 20 relaxation rates recorded over 2 orders of magnitude of magnetic field. So doing the analysis is not trivial in this case. The reason for that is that when we move the sample with the shuttle, then we don't have a probe. And so we have to take into account at least a minimal relaxation matrix that will account for the efficient cross-relaxation pathways. And so it really relies on a good understanding of spin dynamics due to relaxation over a range of 2 orders of magnitude of magnetic field. So if you want to have some details about this, check this nice paper by Nicolas Boly-Coulon and Samuel Cousin. So now we analyze all our relaxation decays together at low field. And so you can see that here 2 fits at 4 Tesla and 0.3 Tesla. And you can see that we reproduce the decays quite well. And we don't make any assumption about whether the decay is mono-exponential or multi-exponential. And at the same time, we analyze high field data, so transverse relaxation rates, the NOEs, and you can see that the fit is pretty good. Now, it's more difficult to represent the R1 fit in this case because we expect, because there are cross-relaxation pathways expressing themselves during the relaxometry experiment, we expect to have deviations between the relaxation rate and the decay rate that we will measure. So if we were to fit those decays with a mono-exponential function, we'd get these orange dots. But the relaxation rate that come out of our analysis is this line. And you can see that they deviate a fair bit. But again, I would expect that from cross-relaxation. The question is just, do we estimate this right? Is this deviation too much or too little? And to validate this, actually, we would need to measure relaxation rates in an accurate manner at fields that are incompatible with a high-resolution, high-field NMR. So how do we do this? Well, we need some instruments that would allow us to detect at high field, but manipulate spin systems also at a low field. And we built such an instrument. Actually, Bruker built such an instrument in a long-term collaboration with us. So the first thing we need to be able to pulse at low field is to introduce a region with a homogeneous field. So the field decays very fast, but a series of so-called ferroshims that are rings of soft magnetic materials compensate the field along the axis and provide us with a nice plateau here at 0.3 Tesla. Now we also need to pulse. So we need a triple resonance probe that is adapted to the right frequencies. And also we had to change our NMR console to be able to, at least part of it, to be able to reach these low frequencies that are beyond the range of a typical high field console. And now we had to couple the high field center and the low field center, and we use that with actually our sample shuttle. So now we have a two-field spectrometer where we can polarize and detect at high field, but can also manipulate spin systems at low field. So we measured relaxation rates with this system, and indeed, with the two-field system, we obtained relaxation rates that are significantly higher than the relaxation decays that we had with relaxometry. Now, what are the relaxation rates that we obtained from the analysis of relaxometry, accounting for cross-relaxation pathways? But actually, they correlate extremely well with the accurate relaxation rates measured with the two-field system, indicating that this understanding of the whole spin dynamics during the relaxometry experiment is not so bad. We understand what is going on, and so now we can look at the data. What do they tell us in terms of dynamics? So the first model we introduced was really a simple extension of model 3, considering that we have three types of independent motions. One is overall tumbling with a single correlation time tau c. Another one is meteor rotation, which is represented in a model 3 manner with a single adjustable parameter that is the correlation time for meteor rotation. And then for the motions of the meteor group axis, then we introduced a model 3 type correlation function with two timescales for fast and slow motions and accompanying other parameters. And actually, we can fit all these parameters, at least in a subset of these isoleucine residues. So two other parameters and three correlation times. We find correlation time for meteor rotation that is of the order of 10 picoseconds. And then for the motions of the meteor axis, we find some fast motions around 100 picoseconds and some slower motions in the low nanosecond range. Now, I mean, this is already quite fantastic, probing motions about over 3 orders of magnitude of correlation times. However, these relaxation rates will not tell us what exactly is the motion that takes place. And to do that, the best way to actually look at the motions and analyze them in detail is to look at molecular dynamic simulations. So what we decided to do is to team up with Raphael Buchweiler and his team and analyze the molecular dynamic trajectory and decide in very simple first zero order approach that if there was a good agreement between the parameters of the MD trajectory and relaxation, which happens sometimes but not all the time, then we could look at the MD trajectory, consider it was validated by relaxation, and describe what was the type of motions that we were seeing. In particular, for the slower component of motions in the low nanosecond range, what we noticed is actually that, for instance, in this sidechain of isoleucine 36, we had 7 of the 9 possible rotameric states for chi1 and chi2 angles that were significantly populated. And if you look at the decay of the autocorrelation for chi1 and chi2, you see that decays in the low nanosecond range. So what we actually think that we see here with this low time scale are actually rotameric transitions of both chi1 and chi2. This is the case for isoleucine 36. In the case of isoleucine 44, for instance, all we see are chi2 transitions. We don't see any chi1 transition. So if we look, for instance, in this region of the protein, we see that we have a probability distribution for this low component of the motion that overlap quite well between these two sidechains that are very nearby. And actually, it's not that far from the probability distribution also for slow motions for this beta-1, beta-2 turn that is also nearby, indicating that, well, maybe there could be some sort of motion, maybe some breathing motion that take place in this area of the protein. So, I mean, this is all well, and I could stop here, but if I have a few more minutes, I would like to show you something that didn't work with this approach. And if you look at the very end of this paper that I cited earlier, you will see a figure that looks like this, where we measured CSA dipole cross-correlated cross-relaxation rates, so looking at this for the CSA of carbon-13, and calculated it from our analysis. And we think that we can actually estimate it quite well from our analysis of all these relaxation rates. However, you see that our calculated values overestimated by about a factor of 2, both the longitudinal cross-relaxation rate and the transverse cross-relaxation rate. And this is puzzling because these expressions are very simple. I mean, they depend on the CSA, and these CSAs have been calculated with DFT many times, measured with different methods. So it cannot be the CSA that is wrong by a factor of 2. The only thing that can be wrong is the spectral density function. So this was complicated because we had to think of maybe going beyond this model-free type of spectral density function. And this required quite a lot of work. I have to say the reason why we did this work was because of confinement due to the pandemics, and a very smart graduate student, Nicolas Bolik-Coulon, decided to actually tackle this problem because this was something MRI could do from his home. And the first thing we did is a little bit of a literature review of what existed before model-free. And in this case, you had a lot of different types of motions that were described and for which we could get correlation functions and spectral density functions. So diffusion on the cone, well, in this case, it's fairly adapted to describe meteor rotation. Rotameric jumps, well, we know from our previous investigation that this is definitely something that is going to be interesting, describing so discrete, infinitely fast jumps between different orientations. And also wobbling in the cone could be quite useful, somehow less so. Okay, so model-free was great because when it was introduced by Lipari and Szabo, it was saying, well, don't fight about what type of motion you have. You can nevertheless say something quantitative about your motion. You can have other parameters, effective correlation times, and you don't need to spend time fighting whether you have diffusion in the cone or wobbling in the cone. However, now something that we have 40 years later that people didn't have are good quality molecular dynamics trajectories. And so we can look at these molecular dynamics trajectories to actually pick up the right models of explicit motions to analyze relaxation in these side chains. So here, for instance, I come back to isoleucine 36, and this is a slightly more recent MD trajectory. You can see that several rotameric states are populated. But what is really important is if you look at these trajectories, you can see that the jumps between the various orientations are really instantaneous. You have barely any point in between. So really, rotameric jumps is a good way to represent these motions. So maybe we can start with, we can actually look at these models that were introduced many years ago and refresh them by combining relaxometry measurements, molecular dynamic simulations. So what we want is going to describe this correlation function that you see here is going from the lab frame to the interaction frame, say, of this dipole-dipole interaction. So we do this with a set of frame transformations going to the molecular frame. So this is overall tumbling. Then to a local frame to get an orientation of the residue, that in which we can place the rotameric frame that will describe what rotamer state we're in. Finally, the system frame in which we will be able to describe meteor rotation, and finally, the interaction frame. So let's start with a simple case. Simple case is isoleucine 61. Molecular dynamic simulation tell us that we have only 2 rotameric states that are populated. So actually, we need very few parameters to describe explicitly these motions. What we need is a diffusion constant for the meteor group rotation and the exchange rate between these two positions. So basically, one population and one kinetic constant. So now we can compare the fits that we have either for our old extended model free approach here with dashed lines or explicit models. And you can see that they agree very well. The two lines are almost on top of each other. However, when we look at CSA dipole cross-correlated cross-relaxation rates, and we use those for cross-validation, we do not fit them, you see that naturally they agree very well with the explicit model, much better than it did with the extended model-free approach. And the parameters that we get make sense. We have methyl group rotation with the correlation time of the order of 15 picoseconds in good agreement with our previous analysis. The population that we get is actually spot on in agreement with the MD. And the kinetic constant for the exchanges of the order correspond to nanosecond transitions that totally make sense. Of course, it didn't work that well for all the side chains, but I'll show you a very complicated case. It's isoleucine 36. If we want to explicitly represent jumps, my goodness, you have dozens of rates to consider. So we had to make a series of approximations. First, we only considered transitions between the major state and the minor states. And we also had to set the populations of all these minor states. Nevertheless, we still have 9 parameters to fit, and you'll see that this may be a bit too many. However, you see that, again, the fit is pretty good for all the high field rates and the longitudinal relaxation rates obtained with relaxometry and high fields. But again, the fit between, well, not the fit, sorry, the agreement with cross-correlated cross-relaxation rate is much better with the explicit model than with the extended model-free approach. However, this is a drawback. We just have too many parameters in our fit, and you see that we do not define well at all the different parameters that we have for this model. So clearly, in this case, there is not enough information. We do not have enough precision, and we do not have enough information to really fit all these parameters. So what this shows us is that in simple cases, these explicit models are very good. But in more complex cases, we need more information. I think the place to look at for more information will be to synergize more molecular dynamics simulations and relaxation. And we're starting to work on this. But overall, the agreement now between the cross-correlated cross-relaxation rates and that they are calculated from the model and those that are measured, you see, is not perfect, but it's much better. Again, we do not fit this data, and you can see that the improvement is very significant. Okay. So what I showed you in this second part is that we can use actually relaxometry to probe the spectral density function over a broad range of magnetic fields. This allows us to analyze motion and identify motions in low-nanosecond regime. The analysis is tricky, and we could validate it with the use of our two-field and mass spectrometer. And quite importantly, having all these relaxation rates and wondering what should I do with them and trying to analyze them has showed us that we had to actually go beyond typical model-free approaches and introduce more explicit models of motion that take into account, in particular, the anisotropic nature of internal motions. So let me briefly thank people. I will go very quickly, but I would like in particular to talk about junior people in the group. So a lot of the work that I presented to you was done by these two graduate students, Samuel Cousin and Cyril Charlier, and Pavel Kadejavec was a fantastic postdoc. All the theoretical analysis was done by Nicolas Boly-Coulon, which just defended his thesis. And some of the relaxation rates that I showed you were recorded by Milan Zashla, who was a postdoc in the group. I thank all my colleagues at ENS and elsewhere, in particular groups of Raphael Bruchweiler and Fabio Sterpon, Guillaume Stiernemann, and Damien Lage. And of course, everyone at Bruker who has worked with us for now over a decade. And I thank you for your attention.